Exploring Time Series using Interactive Graphics by Andrew McDougall and Diane Cook, respectively of Department of Statistics, Rutgers University, and Department of Statistics at Iowa State University. Correspondence to mcdougall@stat.rutgers.edu. In this video, we look at exploring univariate time series with traditional time and frequency domain techniques. In particular, we focus on incorporating graphical diagnostics such as periodogram, parallelograms, lag plots into an interactive framework. The program XQZ is written in C and the X window system and represents a developmental stage in our research of new methods for time series. To initiate XQZ, we type XQZ and the name of the data file we wish to look at. This will bring up what we refer to as the data module, which consists of a plot window and a separate control panel. The data module has functionality for visualization and structural manipulation of the input time series. In this case, we're looking at Canadian unemployment monthly data from 1956 to 1975. This is given in Andrews and Hertzberg book, 1985 book, data. The data shows some obvious visual features which we shall now explore using the control panel functionality. Visual manipulation of the series is achieved by scaling, which expands or contracts the time axis, wrapping, which is used in conjunction with scaling, where the series is allowed to wrap upon itself as the time scale is increased. Shifting consists of moving the series left or right across the plot window screen. While these may be used to enhance the visual diagnosis of the series, structural actions will actually be needed to induce stationarity in the series. Here we have included the Box-Cox family of transformations, which may be used for variance stabilization. In addition, differencing may be used for simple trends or seasonal components. Derived visual diagnostics, such as lag plots, can also be used. Lag plots consist of plotting xt versus itself, but at delayed time. So we will be looking at xt versus xt minus k at different values of k. These are useful for detecting particular lags which have high order correlations. As we cycle through the lags, we note strong correlations occurring at lags 1, 2, and 12, which of course is not unexpected given the nature of the series. Closer inspection of the series would also suggest a non-stationary variance. Box-Cox power transformations may be useful in this regard. This family of transformations is obtained by moving the power scroll bar back and forth. We can also look at common transformations such as the identity, which there has no transformation, square root, and log. And from the series and lag 1 plot, it would seem that square root might be a reasonable choice. A simple difference can be used to remove the upward trend, but we shall first consider scaling and wrapping actions. The actual points can be shown on the plot by pressing the points button. This will be useful with the scaling actions. With wrap on, we can observe the periodic nature of the series coming in and out of phase. This effect is more apparent when a simple difference is used. Shift may also be used to move the wrap points back and forth, and this has a visual effect of actually rotating the sequence of points around. As we go back to the difference series in the full view, a more subtle feature of the series is observed in that the second half of the series is not equally variant about the zero axis, in contrast to the first half of the series. Given the strongly periodic nature of this series, we now consider the frequency module, which is invoked by pressing frequency on the main. The initial plot shown is the normalized periodogram of the series as it currently exists from the data window. That is, the first difference of square roots of yt. In this module, we have incorporated some standard functionality such as the log spectrum on a dB scale, weighted periodogram smoothing options. These have no effect until the bandwidth is increased. The bandwidth number 2 represents an averaging over 5 periodogram ordinates placed symmetrically about each frequency ordinate. The arrows may also be used to examine individual bands or to increase and decrease the maximum bandwidth. Identifying the frequency of each peak is available by holding the right mouse button and sliding the pointer across the plot. The out-of-date button labelled off can be used to link actions in the frequency and data windows, in the same way that the lag plot is automatically linked with the data window. We now will reconstruct the data as we see it in the data window and watch the effect in the frequency window. Because of the trend present in the original time series, we observe high power near the zero frequency. Interestingly, the normalized periodogram, which has bandwidth 0, shows a large peak near the zero frequency, but not actually at the zero frequency. It has a frequency approximately 0.01. It can be seen. We would attribute this to the very low cycle present in the original data series. The effect of the square root transformation is slight, but does increase the low frequency peak of the first peak marginally. This can be seen. The presence of the small peak corresponds to a harmonic of the 12-month seasonal cycle. The effect of the harmonics is more pronounced when first differences are taken of the series, or the square root of the series. We now will use a seasonal difference at lag 12, which appears to have removed that 12-month seasonal component. the series now appears to be closer to second order stationarity and in the next section we look in the time domain approach. The correlograms provide a simple graphical diagnostic for assessing autocorrelation structure, and these may also be used for determining Box-Jenkins types models. We shall mainly focus on the ACF and PACF type diagnostics. The ACF is shown in the top plot, the PACF is going to be shown in the bottom plot. Under the null hypothesis, we can generate two standard error limits, which can be obtained by pressing the SE button. Proceeding as before, we can observe the effect of inducing stationarity in the original series using the correlograms. So when we go back to see the square root, and then the first difference, and then a seasonal difference at lag 12. The final result provides a pattern which shows that it may be plausible to fit a seasonal moving average of lag 1 model with some short-term correlation structure shown by the lag 2. The current modeling treatment here, however, represents more of a research interest of ours concerned with recursive estimation of ARMA models. However, we can observe the effect of fitting an autoregressive model of order 2 by pressing the AR right arrow key twice. In this plot, we see that the two autoregressive parameter estimates, computed recursively over time, the first parameter is essentially 0, whereas the other parameter appears to converge to a steady state value. The correlation structure of the residuals that resulted from fitting this model can be observed in the correlograms via the residual button. Here we see that the short-term correlation structure has been partially captured by fitting an AR2 model, and a full seasonal model could then be examined. Finally, we show that the residuals from the fitted model can also be examined in the frequency module. By pressing the ARMA Resid button, we will obtain the residuals, periodogram in this case, of the residual series. Having completed part of our analysis, we may wish to examine further series, and this may be done by using the New File button on the main plot window. This consists of a one-line editor which allows the new data file to be entered, an output file editor which allows us to save output that is of interest to us, and also a history file which acts like an audit file and would record important events that we use in obtaining stationarity, for example. Since this is being filmed in Iowa, to conclude this video, we would like to emphasize the intention of XQZ. Rather than encompassing all possible diagnostic methods, we have concentrated on the important dynamic graphics tools that appear to be useful in exploratory time series analysis. We have also tried to keep the program as modular as possible so that modifications or enhancements may be incorporated in a relatively straightforward manner. And lastly, the main objective of XQV is as a flexible research tool in applications such as recursive estimation, multivariate exploratory time series.